von Cyberus, 5 Jahre immerhin schon wieder unterwegs als Startup, was schon die ersten Reife gerade erreicht hat und mit 5 Jahren hier schon im Virtualisierungsbereich und Software-Security-Bereich im Markt agiert. Werner, wollen wir loslegen? Shall we start? And then we'll see who will find the live session or later the recorded one. And I think the floor is yours. I'm happy you're here with us. Thank you for making yourself available. Thank you.
Well, thank you for joining this webinar. And let's see, switching worked. Okay. It feels kind of awkward, of course, talking to just a couple of people, and maybe some people watch the webinar and the video online. If there are any follow-up questions that you cannot ask today, just shoot me an email and I'll get right back to you and hope to clarify whatever is there. I planned to start with an introduction. So who is this guy, Werner Haas, that is talking to you anyway? And of course, that's kind of, okay, here it switches. That's Jan Tiedemann, he knows me, of course. The other guys do not. I am a Franconian guy, so it's not quite the Munich region, but at least it's in Bavaria. Grown up, educated in Franconia. I live close to Bamberg. What you see here is a nice castle that is almost in walking distance. Well, if you're good at hiking, it's about 40 minutes walk by foot to get there. Studied electrical engineering in Erlangen and had my first professional jobs there as well, working for Lucent Technologies in the optical telecommunications department. So what makes me talk about computer architecture here? The reason for that is that I spent over 10 years at Intel, some of those years in Intel USA, in Intel Labs, Jones Farm in Oregon, working in the group of Richard Ulick, who is the guy behind pushing virtualization technology into Intel architecture. And after I left Intel, I reunited with a couple of colleagues from the Intel days in Dresden, where we worked for FireEye on a hypervisor solution for security purposes. And then the Dresden development site got shut down. And as Peter mentioned, we decided to start our own company, Cyberus Technology. That's almost 5 years ago. And our claim to fame is the Meltdown and Spectre side channel transient execution stuff that got us well known way beyond what we could do with our virtualization technology. And having said that, those side channel attack things, they are just some kind of hobby activity that Thomas Prescher and I stumbled across when we had time to spare, and we disclosed it to Intel in 2017, roughly at this time of the year. And since then, I was traveling the world, talking to people about processor architecture, computer architecture, and today we'll do the same. And I will want to take you on a journey through time and space, and be prepared. I mean it literally when I talk about space travel. But first, some time travel. What you can see here is Hammurabi steel, and it's not quite Iron Age, but I want to talk about the iron law of processor performance, so that's close enough. And Hammurabi steel is probably the first written law known to mankind. And the iron law of processor performance is also some very fundamental law that helps us understand what is going on in computer architecture. So when we talk about performance, typically it is associated with having less time for a given task. And of course, you can already expect when we talk about performance, there's some work associated with it. And everybody knows from experience that when we talk about processor performance, that frequency plays a role here. And since frequency is number of cycles per time, but on the left side, I have defined processor performance as time that is required per task. I need the inverse. in order to get this stuff right. And as you can see here, if we measure the work, it's typically the number of instructions that is required for a task. And on the right-hand side, the inverse of the frequency definition, which is time per cycle. And if you look at the formula close enough, you see that there is a term missing here. And this missing term is called CPI, or cycles per instruction. And if you look at the equation, we have the instructions on top, we have the instructions on top and on the bottom, so they get away. We have cycles on top, we have cycles at the bottom, they also go away. So we have time per task, so the left-hand side and the right-hand side, that's okay. And this basic law, that pretty much explains everything that I'm going to talk about in the next half hour or so. So moving on a little bit, what are we going to do with this formula? What I did for another talk, I just took the Spectre paper that won an award for best research in cybersecurity, and calculated, since it was a security conference, just calculated an MD5 hash on top of that. And the perf stat command on the left side, that's just in a Linux system that gives you some basic statistics on the execution of such a thing. And if I do that with a computer that I'm using right now in order to talk to you, it gets to roughly 3 million cycles. It requires roughly 4 million instructions. We have 500,000 memory reads. And if we calculate that, 4 million instructions and 3 million cycles, we have 0.75 cycles per instruction. So that's just some value. I could have picked something else, and those values, they vary a lot. So if you do that on your own machine, if you do it twice or 3 times in a row, you'll see that there's quite a lot of fluctuation. And I generally picked a pretty conservative number in the way forward. It's not meant as pure benchmark. It's just to give us an indicator of what is going on. If we move back in time, and again, that's a gross oversimplification what I'm going to do right now, but it just I'll show you the importance of this CPI term and some other parts of the computer architecture. The ancestor of my notebook here is probably the Intel 386 microprocessor. And if we look into the datasheet, we see a nice timing diagram with all the different signals when it comes to memory accesses. And the 386 microprocessor, it did not have any caches on the CPU. So whenever the processor needed data, it had to go out to memory. And the caches that were present on those boards, they were external to the CPU chip. And I will highlight the important parts of this timing diagram. We start from idle phase, and here is the number of clock cycles. And after 4 clock cycles, we see that the data is ready at the processor. And if we compare that to the notebook here, 4 clock cycles latency, that's pretty much the latency that you have with a level 1 cache on a decent performance Intel CPU here. Of course, with smaller CPUs, the numbers are different, but for all the PC class CPUs, 4 or 5 clock cycles, probably 3 cycles if you have an older Atom, that's the latency that we are dealing with. So maybe you're curious, what made me pick this background picture of the moon and Mars? Let's just assume that the processor resides on Earth. That's where the actual stuff happens. And if we go to moon, that's something like 1.3 light seconds distance. And if we have to go to main memory in a modern computer, we would have to go all the way to Mars to find the data. So that's the kind of relationship. If we are the CPU on Earth, the level 1 cache is the moon, and the main memory is on Mars. So this already tells you the NASA spends big dollars, and the European Space Agency big euros in order to get to Mars. And it takes forever to get there. And in computer architecture terms, it's the same thing. And if we take the numbers and compare them, and again, that's a gross oversimplification what I'm doing here. Let's assume the 386 has a clock frequency of 20 megahertz. We have the 4 million instructions, the 0.5 million memory reads. We have the latency of 4 cycles. Taking those numbers, we come up with a CPI value of 0.75. And if you look at the technology evolution of the last 30 years or so, the algorithm itself doesn't change. We still have 4 million instructions. We have 500,000 memory reads. And with a modern CPU, we have something like 100 at least cycles in order to get the data from Mars or from main memory. And if we calculate the total number of cycles, I just add 500,000 memory reads times 100 cycles. So we end up at more than 53 million cycles for the same task. So those 30 years of processor evolution brought us a 100x increase in frequency. And out of that 100x increase in frequency, which translates to processor performance, it gets reduced by something like, or to something like 1/6, just because the CPI value also increases from 0.75 to 13.25. And obviously that's counterintuitive, because we all know that in the last 30 years, process performance increased more than 100x, and not just by something like a factor of 6 that remains when we compare the CPI values and the frequency. And what led to that enormous increase? We got rid of this memory latency. And what happened here, the computer architects, they introduced caches, and they are meant to be invisible. And if you look at the iron law of compute performance, it's pretty much like the Einstein formula, E equals mc squared. It looks very innocent, but in practice, the devil is in the details, and it requires quite a bit of understanding to get into the intimate details of that. And the same thing here, if you look at the caches that are meant to preserve the CPI value at 0.75, because we reduce the latency here, with Einstein, we have those black holes and whatever invisible things that are not directly observable from Earth. And what you can see here in the background, that's a so-called gravitational lens, because although we cannot see the object, its gravitational effects bends the light, so we can conclude that there is something in between. And in this case, there is a galaxy cluster somewhere in the line of sight between us and the bright object that led to those two bright points here in the picture. And this gravitational lens introduced those arcs here. So whenever we try to hide something, the universe is just smiling at us and telling us there is no such thing as something purely invisible. And that's what we had to learn the hard way when we came across those side channel attacks. Caches are meant to be invisible, but if the bad guys try to detect something there, they will surely find it. So let's switch gears a little bit. Side channel attacks are pretty much old stuff. Let's look at the disclosure of the information that is also important if you want to access secrets. So what we have here, that's a picture of an actual Turing machine. And a Turing machine is just a mathematical model for the way we formulate our algorithms. And what we have here on the left, we have a spindle with data. The data gets fed to this processing unit here where the data is being read. So it takes a snapshot of the data, it processes it, and maybe writes it back down. And what you can see here, that's purely a linear data flow, what this Turing machine is built upon. And the question is, if we have this Turing machine, how do we get performance? And in the iron law, what I introduced, it was cycles per instruction. And of course, you can build the inverse value again, like what we did with the frequency. We can look at and the inverse value of cycles per instructions, that's instructions per cycle. So when we want to increase the performance, we can either decrease the cycles per instruction or we increase the instructions per cycle. And what kind of means do we have in order to increase the instructions per cycle? So with CPI, it was easy. We just reduce the time that we spend on memory accesses, and then the cycles per instruction on average goes down. We also have other stuff going on. We have arithmetic calculations, we have control flow operations, and so on. And they would not benefit at all from caching. But what we can do here, we can increase the number of instructions per cycle. And there are two ways of, well, there are a couple of ways, but the two straightforward ways of doing that is pipelining it. And the second one is superscalar. So if we start with pipelining, feeding the data from the left spindle here to the camera that reads the data from it, that is completely independent from, well, not completely, but largely independent from writing something new here to the right-hand side. Taking a photograph is independent from processing it, and that's meant by pipelining. We just split the processing step into multiple parts. And with every pipeline step, we increase the number of operations that is in flight. So if we have a 5-stage pipeline that is typical for the low-end microcontrollers, just by having a 5-stage pipeline, we have increased the performance roughly by a factor of 5 if you look at the simple formula. And if you look at the high-end CPUs, the one that I use here in my notebook, we are something in the 15 pipeline stage range with our CPUs. And the second one, superscalar, that just means that we duplicate this processing unit in the middle here. So instead of just reading 1 0 or 1 1 at a time, we can read 2 of them at the same time. And that's pretty much like the way you would increase performance if you ran a factory. If you need more output, you just build a second factory right next to the first one. And if it's the same factory, you can double your output. And that's the way it works also in a CPU. Now, this is the Turing machine is a very basic and generic model of computation. Maybe you recall what I did the last time when I talked about some fundamentals in generic terms. I came up with a picture of Mars. And let's just try it again and look at the Perseverance robot on Mars, and let's see what we can learn this time. The last time I also talked about the MD5 hashing algorithm. And if you look closely enough into the implementation of the algorithm, you find a step where the data has to be padded to get 512-bit chunks. And if you look at it in some simple Python code, you might come across the following 2 lines of code. While the length of the message modulo 512 is not equal to 448, we just append a 0-bit to that one. And that brings us in the end to 512 if we started at something that was lower. So it just increases it until we have those 448 data bits, and then the algorithm adds 64 bits, which leads us to the 512-bit in the end. And what we saw on the slide before with the Turing machine, it likes sequential data flow. We had the spindle and the tape does not like discontinuities. But if we look at the code here, that's anything but simple sequential processing. So let's look at those control flow discontinuities or the jumps that we have in the algorithm and see where we have those nonlinear things. the first one that we have is calling this length function here. And in more generic terms, that's a direct jump instruction that makes us move along the tape. And it's very easy to detect at decode time. As soon as we see something that looks like a jump, we know, okay, it doesn't make any sense to continue in a linear fashion. The problem is we don't know yet where to continue. In the very simple case, we have an absolute address where we can move the tape to. In some more complex situations, we have some offset. For example, in position-independent code, we have to take our current position and add some value. But in general, that's still a very simple calculation. The second jump that we have here is when we come back from the length call here. When we call the length, when we want to determine the length of the message, at some point we want to return to this while thing. And this is an indirect jump. Again, we know almost immediately when we decode the instruction that we cannot continue in a linear fashion. But this time the destination is more complex. It's not a simple calculation. In a so-called reduced instruction set computer, a RISC computer like the ARMS or RISC-V or so, this value is found in a register. With Intel architecture, we get another wrinkle to that because the value is actually stored in memory. So we get a memory access whenever we want to have a return in our instruction stream. And of course, the last control flow discontinuity or non-linearity in our control flow is the while function itself that started this whole mess. And that's a conditional jump instruction. So when we see this while or the corresponding compare function in assembler code, we don't know yet whether we are allowed to continue in a linear fashion with the next instruction or whether we have to jump somewhere else. So we have to wait until the command is fully executed before we know whether we have to act or not. The destination, however, is as simple as in the direct jump case. We just have typically position-dependent calculations. So we take the instruction pointer and add some offset, and that brings us to the point where we shall continue. So when we look at processing algorithms in a Turing machine, we see that there are basically two main problems to solve with every instruction. And since there are two different problems, it's not surprising that we find two different hardware structures that take care of this problem. The first one is the branch history table. It just looks at the instructions and tells us whether there was a discontinuity before at this point or not. And the second one, the branch target buffer, it tells us where to continue. And those two structures, by the way, the names are not canonical. So whenever you read a paper or instruction manual or so, you got to be careful what the authors refer to. But in principle, both functions exist in all computers. And those two things, they are basically also just caches that remember what has happened in the past. And like with the gravitational lens, you cannot truly hide those things. If you look here at the picture of Perseverance, what we can see from the camera that the robot just took a circle. So the state of the robot hasn't changed, but we can see that it has done something. And why has it done something? I told you that Mars is something like, it's over 180 seconds, I think, is the closest distance to Earth. So if we assume that the operator of the robot sits here on Earth, it would have to wait a couple of minutes before he sees the reaction for that. So what we do here, or what the aerospace engineers do here, they let the robot continue for a while and then revert back. And that's exactly what's happening in the CPU. it is allowed, even though it detects here at decode time that something non-linear is happening, it is allowed to continue, and it can revert back to a safe state in case something unforeseen happens. So this brings us to the whole Spectre class of things. And I was delighted when I was looking for pictures that I found a Spectre in the sky. And I told you in the beginning, we are taking a travel through space and through time. And this is the space picture that I have for Spectre. And if we plug in the numbers, and if you just look at the branch history table, which is associated with the first version of the Spectre exploits for transient execution attacks. If you look at the Spec CPU 2017, that's a standard benchmark to measure CPU performance, we have roughly 20% branches. If you look at a modern day Intel Ice Lake CPU, we have 5-way superscaled instruction decoding, so it can decode 5 instructions in a single cycle. That means with 20% branches, with every cycle, we have roughly 1 branch. And if something goes wrong, the processor requires approximately 17 cycles to recover from a misprediction. So what choices do we have here? If we want to fetch 1,000 instructions, if we had perfect predictions, we have 1,000 instructions, we have 5 instructions per cycle, so we require 200 cycles in order to get those 1,000 instructions into our processor. If we want to avoid this misprediction, this false speculation, because we know, oh, there are evil side channel attacks possible, so let's just prohibit them and wait for the branch outcome. We have 1,000 instructions, and since there is a branch instruction in every cycle with this kind of computer architecture, we would require 17 cycles in order to wait for the outcome. So the time to fetch those 1,000 instructions would increase to 3,400 cycles, or by a factor of 17. That's clearly unsustainable. You cannot sell either a CPU doing that kind of philosophy, or you cannot sell software that is programmed this way because it disables the branching. So what the CPU does, let's just assume we have 99% accuracy with our branch predictor. We have 200 cycles. At 99% accuracy, we have 10 misses. With every miss, we have 17 cycles of penalty that we get from the misprediction. So in the end, we have 370 cycles here. And this already tells you, when people say, oh, whatever, 99%, 98% accuracy, it doesn't matter. Well, the percent numbers are misleading here. So if you look into academic papers, they talk about misses per kilo instructions, and that's what we see here. When we have 10 misses per 1,000 instructions, we almost reduce the performance of our computer by half, from 200 cycles to 370 cycles. So this tells you how important branch prediction is in any CPU in order to get decent performance. And a word here, people complain about Intel and AMD that they are overly aggressive and they were just too eager to make money and didn't take care of security things. What we see here, this has nothing to do with processor guys being overly aggressive. The same rule here holds also for RISC-V with a simple 5-stage pipeline, for example. The main difference here is that the branch misprediction penalty is not 17 cycles. So the attacker has a lot less time to do stupid things, and that's the reason. It's not the branch prediction itself that is the culprit. We have seen from the model of the Turing machine that branch prediction itself is inherent in the very basic abstract model that we use there, namely when we use a tape that is fed into the processing unit. That's where the branch prediction requirement comes into play. And of course, if we want to have at least some performance, because we have pipelining and superscalar execution. So that's the version 1 of Spectre. The version 2 of Spectre, we have a second unit in the branch prediction unit, the branch target buffer. And the problem there is, if you look at the branch predictor, it is a hotspot. So if you took a thermal image of your processor and you see the hotspot, it's pretty likely that this will be the location of your branch predictor, because it has to be used in every cycle and it has to be used for every instruction that the processor is about to process. So this makes it a very hot part on the chip. And a couple years ago, or over a decade ago, people looked at reducing the energy that is being spent in this BTB unit. So what we see here in this diagram taken from that paper, we see the loss in instruction per cycle, and we see the tag length in bits. Tag length, I told you that branch history and branch target modules, they are basically like caches. So you store something there and you may make a mistake because you do not have the full information. And what is being used to look up data in the caches, that's a tag. And instead of using the full address, here the number of bits is reduced to, here to 7 to 8 bits. And at 8-bit tag length, instead of the full length, we see that there is no measurable impact on performance that we see here. And of course, in this case, the left-hand side goes to 21. If you reduce from 21 to 7, we have 1/3 of the bits that are being used for the tag comparison. So we save an enormous amount of energy there. And saving energy helps us reducing the heat that is generated in this area of silicon. And this is the problem of all heuristics here. What we see here, that's average performance. And it works very well in the average case. But attackers, the bad guys, they are anything but the average guys. So they explicitly work outside the rules that apply to regular programs and try to create conflicts here with a tag length in order to make the processor jump to a different place in the instruction stream. And of course, the processor will realize its mistake after those 17 cycles and correct it. But by that time, it's too late and it will already have disclosed information. And this disclosed information can then be leaked to the outside via standard side channel attack means. So that's a rough overview of the two Spectre variants. And you might be curious, why didn't we see that before? And if you are some astronomy aficionado, I don't know, have you ever seen this Spectre ghost in the sky? Chances are pretty low. And the reason for that is maybe it's in the southern hemisphere and we cannot see it from Munich. Well, no. What you can see here, that's in the Cygnus constellation, and that one is well visible in the northern hemisphere. So the second reason might be that this little ghost here is too small. Well, no. This thing here has roughly the size of the full moon in the sky. The problem here that you guys and me neither, that we didn't see it, is because it's too faint. So you need a lot of time in order to detect or to capture enough photons in order to come up with such a beautiful image. And the same applies to the side channel attacks. So if you look at Spectre and Meltdown and the question why those vulnerabilities have not been discovered, let's say, in the 1990s with a Pentium processor, the reason is that the modern CPUs with their complex memory hierarchy and out of order processing and so on, they just make it a lot easier to come up with those attacks. And out of order processing is by no means required in order to do that. On the slides before, I never talked about out of order processing. But what out of order processing gives us, it extends the window where an attacker can play tricks with a computer architecture. And that is the main reason why the big CPUs are more vulnerable to those attacks than the smaller ones. But in a processor course, training course that I taught a couple of months ago, I had my students, or I showed my students a simple 5-stage processor pipeline, and we were able to design that pipeline in a way that we could also have a side channel attack on this very simple in-order 5-stage CPU. Well, this brings me basically to the end of my talk. I was talking about security and computer architecture, and Peter asked the question whether they are a contradiction or not. I started then with the iron law in order to explain what's going on in the processor, and I used Hammurabi steel as a very fundamental and an old thing that applies. From that, we looked at the cycles per instruction term of the iron law that brought us. Is there a question? I hear some noise here.
Well,
okay.
Thank you. Thank you.
No, I just continue. I just thought that there was a question.
Please go on with your summary.
This brought us to the CPI term, and I talked about caches that are meant to be invisible, but like the black holes or the heavy objects in the galaxy, they have side effects that you can spot here with a gravitational lensing effect. From the CPI term, if we take the inverse, we come to IPC, or instructions per cycle. So we looked at the Turing machine and ways to improve performance via superscalar processing and via pipelining. And the inherent problem that comes with that is the branch prediction, where we have to predict where to continue on the tape. That is the basic abstract mathematical model of our computations. And this brought us in the end to the Spectre exploits and the darker corners of the universe that were also advertised in the announcement of this talk. And the question is, what can we do against that? And if I'm allowed to rant a little bit, as we have seen, the problem lies in the Turing machine and whatever we did in order to squeeze performance out of that. And what we need, we have to look at the memory architecture that plays a huge role when we look at the iron law and especially the cycles per instruction. The problem is we have no information about what is being stored in memory. And if we had at least some meta information that the processor could use in order to validate or in order to perform some checks, then we could mitigate a lot of those issues. The problem there is nowadays, if Linux doesn't run on such hardware, the hardware has lost. And the other way around, with Linux, it just assumes that everything is being done in the translation look-aside buffer that is used for memory protection, and you cannot easily come up with new things. So you would have to have hardware-software co-design in order to have some good improvements there. And I'm actually a little bit annoyed because I wrote a proposal to the German Ministry of Research for starting a research center on computer architecture, especially with respect to improving security. And the answer was not, well, it's a crappy proposal, or those ideas are not thought out enough, or whatever. They just said that there is not sufficient interest or value for the German industry in such a thing. And that's a comment I also heard back from the days at Intel, where they said, well, we could increase security, and you have very nice proposals there, Werner, but nobody is going to pay for it. And that's the problem that we have here. In principle, we could do that also on computer architecture side in order to improve our systems. But in the beginning, on the title slide, no, I don't have it here. I showed the castle next to my hometown, and I showed the Frauenkirche in Dresden. And what you see there, it's Baroque architecture. And if you look at the Intel architecture and also the high-end CPUs that you find for Apple or so, they have the look and feel of some Baroque building. So you just add stuff, you make it nice looking, but in the end, it's just the same old stuff. And what you would need there in order to improve security, you would have to have a building from the ground up that has security in mind. And maybe with you guys down in Munich, at some point in time, we can meet in person. We can have some chat over some coffee or some beer and discuss ideas on how we could get those CPUs in a more secure way and design software along with it, so that we don't have to worry about Meltdown and Spectre and so on. And with that, I'd like to conclude my talk. And if there are any questions from the guys on the bridge, please feel free to shoot them right away. And for those guys watching the recording, werner.haas@cybersTechnology.de. I don't know whether you have the email link also in your meeting announcement, Peter. Just send me an email and I'm happy to pick up any discussions.
Thank you so much, Werner. I will add the email address to the information on this talk, so that I'm sure that the recording will be well received once we have it online. We have this week on Friday, and I tell you this now because sort of the get-together of the cyber community, if you wish, here in the southern part of Germany. So if you want to join, the Security Network Munich celebrates their, the annual assembly, and I just thought maybe it would be great if you could come. I'll send you details later, and you think whether this is worth the while to jump down a little bit further south. Now to the questions. We have a very faithful audience today. While they are thinking their questions, I start with my question, and that would be, from your point of view, Werner, now with, by the way, I love this analogy you used with space and this, side channel attacks and how things are happening in space and how you detect them, indirectly, but they're still happening, and how, subtle it all happens. And I thought this was a very good picture of, explaining how side channel attacks also are occurring. Open source is my question. Do you think that security by design, as you just mentioned in your conclusion, is a way forward by designing those architectures in this open source channel? We have RISC-V, they are a prominent example.
Yes, I think so. And I'm a huge fan of RISC-V. Actually, I started following RISC-V a decade ago when I was still at Intel, when we were working on that. So I have a close eye on that. And I think the only way to get disruptive changes into the community is through open source. I doubt that a closed source CPU developer that comes up with something crazy with respect to security features in the CPU will have sufficient traction in the market to push it out there. Of course, there will be closed source developments for higher performance or so, but I think the fundamentals that we are talking about, and I'm thinking along capabilities. So along with this Spectre discussion, I was in Washington, talked with the NSA people, And we talked about capabilities directly in hardware. And that's one of the things that we can do. And there is a RISC-V development going on in the UK by the Cambridge guys. They are developing RISC-V in that direction. From my point of view, they are not radical enough. I'd like to take it yet another step further, and there are ways of doing that. And we had prototypes at Intel. So Thomas Prescher, he worked on a diploma thesis back then. He's now also a co-founder of Cyberus. We worked on a processor architecture where we had a single address space and we ran Linux on top of that. And with this single address space architecture, we had different protection capabilities, and they are just better. Well, I should be careful with better performance because we did have some benchmark, but it was not conclusive. It was not comprehensive enough. But we have strong indicators that we can get better security, that we can get at least the same performance when we change the memory architecture underneath. And that's a kind of change that is only possible if we have compiler builders, if we have software and OS developers, if we have computer architects all working in conjunction. And I do not see this happening in a closed source environment. So yes, I agree, open source is the way to go. And the indicators that I got from NSA is also that the government agencies would be supportive of such endeavors.
Well, Michael, Jan, any comments or questions from your side?
Yes,
No,
I have a question.
Yeah.
But Michael, you go first.
No, go on, Jan.
The question was just that there's a lot of companies now, or several companies having their own chips designed by others, like most importantly Apple, of course. So are you aware, or do you presume that in these custom designs these things will come up, and that they will try to find their own solutions in their custom chip designs? Is that an aspect of these special cases?
One has to be careful there. So first of all, if you most of those CPU designs, they have very low complexity CPU architectures, and there are just a couple of companies that are building truly high-end CPUs. And if you look at RISC-V, for example, even the highest end RISC-V implementations that I am aware of, they have rather short pipelines. I think the deepest one is it's still in single-digit stages. And by that, they are protected from a lot of this branch prediction stuff, because the window until it gets detected is just so short. The window increases when you have out-of-order processing, because then you might have something in flight that is stalled, and you increase the time period where you can do harmful things on the CPU. But that's not the majority of the chip builders. So that provides some safeguard. If you look at the implementation itself with branch prediction, it's basically impossible to get this thing truly closed. So there were a couple of guys that said, well, you just have to do this and that, and then this Spectre attack is rendered useless. And then you just wait a couple of months, and people came up with another workaround on showing that. Even worse, if you look at the side channels in general. So if you look at Meltdown and Spectre, there are two separate problems. On the one hand side, we have the information disclosure, which is in Spectre, the jump along the instruction pointer that went to the wrong destination. And in case of Meltdown, it was a bypass of the security check. And the second part of that is equally important is the side channel thing, where we had the cache timing, for example. And it is next to impossible to get those side channels completely out of the picture. And by definition, a side channel is something that is not covered by the specification. So there will always be some other side channel there. And I doubt that if you just take IP from different people and assemble them to a new chip, that you get good security properties out of that. It's similar to the traditional security software where you pick some library from here and some library from there, and you assemble your application. And just by combining those parts, some borderline requirements might be violated. So in the end, something becomes insecure. And I think that happens also when you have those chip builders using IP from external providers, where you end up with something insecure.
Okay, thank you.
Michael.
Yeah, maybe one question from my side. So I'm curious, when you're talking about a new architecture, is that then addressing mainly high performance CPUs, or do you think this can also be scaled into microcontrollers for embedded systems? So personally, I'm more interested into systems which are based on microcontrollers. And the question for me is, would it be a future opportunity to go also in this space with a new architecture on the CPU side?
Oh boy. Very interesting question. And yes, it can also be applied to microcontrollers. And in fact, I would argue that there is a better chance of starting it in the microcontroller space than in the high-end CPU space. Let me explain why I come to that conclusion. The reason is that in order to get the decent performance, in order to get those 17 deep pipelines, in order to get 5-way superscalar processing, in order to get out-of-order processing and so on, you need a lot of design experience. That's very complex. That's not an easy task. And in the high-end space, it's also that the processor itself only plays a minor role in overall chip performance. So you need very good memory controllers. You need a caching hierarchy that is very good. You have SMP processing along with it. So that makes it highly complex and not an easy task to come up with a product that can compete with the Intels, with the high-end ARMs, with the Huawei's, with the Apples and so on. In microcontroller space, we can do the same thing. And I talked about the single address space thingy where we use capabilities for protection instead of this page table architecture that dates back half a century. So the foundation for that was laid by IBM in the 1960s, and the seminal paper is from 1970. And that's where all our security is built upon, some stuff that is 50 years old. And this single address space would allow us to combine those microcontrollers with persistent memory. And persistent memory is kind of nightmare for the system software developers because suddenly you have some user space things. You have file system like semantics in memory, but you don't want to have the file system in the way because that slows down the whole thing. So if we came up with some hardware mechanism in order to speed up this thing so that a microcontroller can run completely out of memory, out of this new persistent memories that are about to enter the market, then we could have the ease of programming, making the life for the microcontroller software environment a lot easier, and we could get the added benefit from a security perspective. And if I may add to that, also this whole caching and whatever architecture stuff becomes a lot easier. So what we did with Intel, what we were able to demonstrate, Thomas Prusher and I, that we were able to recover the whole overhead that we required in order to have some shim in between the Linux, the standard Linux software that we ran on our single address space hardware. We were able to recover that overhead by more efficient caching algorithms, because we could increase the level 1 cache from 16 or 32 kilobyte easily to 128 kilobytes. And that's something that I think could also be beneficial when you look at resource constrained environments where microcontrollers come into play, where we could save energy there. So to answer the short answer to your question, actually, I think there are better chances of getting such things done in the microcontroller space than in the high-end space.
Great, thank you very much.
Well, wonderful. I would like to conclude now this highly interesting and also, I think, entertaining session on this topic, on the architecture of computer systems and controllers versus security. So we understand that there's still a way to go, but already some promising paths open. Thank you so much, Werner, for joining and making yourself available, and also to our faithful listeners for joining this talk. It was a very intimate one. I appreciate that you have joined. Thank you so much, and thank you very much indeed, Werner, for sticking to the plan and giving us that interesting insights from your work and from your research. Thank you so much. I hope to see you all soon in our next sessions that will be published on the website of the Security Network Munich. Have a nice evening here from Munich, and talk to you soon. Thank you so much. Bye.
It's been my pleasure.
Thank you.
Thank you.
Thank you. Bye.